Hello guys, how are you all?
Hello, ma'am. Fine, ma'am.
Well, everyone.
Yes, ma'am.
Yes, ma'am. Fine, ma'am.
Okay, fine. Okay. Today we are going to discuss some webinar on physical design, the PD flow, and also the TICL scripting language. So, what are the benefits of TICL language? And like a PD flow, RTL to GDS, how we are going to design some chips. Okay. So we have a, senior PD design engineer here, physical design engineer. So she is working in the industry, and also she is the trainer from past 4 years. She is into the training domain also. Parallelly, she is also working with the industry. Okay, so she is going to take care of all PD related trainings, internship programs, and workshops from now. So, and this webinar is going to handle by her. Okay, so she will start the session, make the session more interactive. Whatever the doubts you have, you can clear your doubts with herself, with her. Okay, yeah, that's it. Christina, you can start your session.
Yes, ma'am. I'll start with it.
Yeah.
I share my screen now.
Yeah.
Is my screen visible?
No.
Okay, just a second. Please let me know if you can view the screen.
Yeah, it's visible now. You
Oh.
can put in a slide share, like a full screen.
Yes, I will. Okay. So before going into the PPT, I would like to introduce myself. I'm Janet. I'm a senior physical design engineer and trainer from Bangalore. I have been working in 5 nanometer and 3 nanometer technology and I have been working from RTL to GDS converted into STA and physical verification checks. So this is my domain. So in this session, I am going to, so there are 5 modules in your advanced physical design course that we are going to start. So what I have planned is I will give an introduction about the VLSI industry and what we will be teaching in each of the module in this course. Okay, so that's how I have structured this PPT. So whenever you're having any doubts, please stop me then and ask. So what is physical design? Can anybody have any idea about that? What is physical design in VLSI domain? Any idea of design domain?
Circuit level to layout designing.
Yeah. So circuit level to layout design. Yeah, that's right. So in terms of in simple terms, we can say that, see, we are going to design an IC. Okay. And to design that IC, there are several steps from the start to the end. Okay. So the first step is getting the specifications of the IC from, all right. For example, if Lenovo or OnePlus okay, let's take an example of OnePlus phone. So in this OnePlus phone, we need
Hello, ma'am.
to handle all the, yeah.
I mean, sorry, I couldn't hear you. Like your voice is breaking. And people are also posting the same on the chat.
Oh, okay.
Yeah.
Okay, just a second.
Mhm. Mhm.
Is my voice clear now?
Yes, ma'am. Yeah.
Okay, okay, then I'll proceed. Okay. So as I was talking about the entire life cycle of an IC, the starting point of this life cycle of an integrated circuit starts from the client's specifications. So for example, if OnePlus phone manufacturer needs an IC for their series of phones that they're going to launch. So what they will do, they will approach our industry VLS experts and they will submit their requirements that, okay, I need an IC for my phone and and these are my specifications. Specifications as in frequency, the power and the size of the chip and storage of the chip. So all of these are called as specifications. So this is the first point where an IC is born. So when the client submits all of these specifications to the physical design domain or the entire VLSI domain, they start and working on the science. Oh, all right. So there are some 7 to 8 steps from this system specifications to the final output. We design engineers will be doing the following part of the so
Ma'am, sorry to
we
interrupt.
of engineers.
Ma'am, we cannot hear you again.
Yes, my voice will break continuously.
Okay, just a second.
Please wait for 2 minutes. We are going to reshare the screen. Just we are facing some network issue. Just wait for 2 minutes.
No problem.
Am I audible now? Is my voice clear?
Yes, ma'am.
Yes, ma'am.
Ma'am.
Okay, fine. So Prashanti ma'am will be sharing the PPT and then I will continue the presentation, okay? Because as I was sharing the screen and also talking, maybe that's why my voice was breaking. So she will share the PPT in 2 minutes. Once she shares the screen, I'll continue the webinar. Ma'am, you can go to the next slide. Okay, so is the screen visible to everyone?
Yes, ma'am.
Yes, ma'am.
All right. Okay, so again, I will start from the beginning. So we were discussing about what is physical design, and somebody gave me an answer saying that it is from circuit level to layout level is physical design. So basically, that is what we will be doing in physical design. But to give it a bigger picture, to add more clarity to it, we have to understand physical design from the VLSI life cycle, from the IC life cycle, from where it is starting and where it is ending. So the start point of an IC comes from the client specification, as I was talking about earlier. So if a client needs an IC, they will approach the VLSI industry and submit their specifications like the frequency, signal to noise ratio, Wi-Fi security, what kind of Wi-Fi security they want, how many memory cores they require, what must be the bearable power, what must be the size of the IC. So all of these comes under system specifications. Okay. So the client will approach the VLSI domain in a VLSI industry and they will submit their specifications. So from there, engineers will start working on that. So there are several set of engineers. So there are around 8 to 10 processes which happens before the input files come to the physical design domain. Okay, so once the specifications are submitted to the VLSI domain, some processes happen and some different set of engineers work on it. And we, the physical design engineers, are the last set of engineers who will work on the IC. Okay. So there is no need for us to understand what the previous set of engineers do, but I will just explain what they will do in the upcoming slides. So once we get the inputs from the previous set of engineers who worked on the IC, we will work work on the files, and we will generate the entire layout of the IC. Layout of the IC as in, you can consider it like a blueprint. So we are making when we are building a house, we will make a top level view, a blueprint of the house, right? Similarly, when we are going to design an IC, this final layout of the IC will be designed by a physical design engineer. And this layout is called as GDS layout. It is a graphical data stream layout. So this is the final output of physical design engineers. So this output only will be given to the manufacturing team to manufacture the IC. So in industry terms, we don't call them as manufacturing team, we call them as fabrication team. So hereafter, fabrication means you relate to it that manufacturing of the IC is going to happen there. Okay. So this is just yeah.
So only here will be the like the digital circuits only. They'll be doing, no ma'am. Like analog circuits all won't come while
We will
doing the physical
only
design.
digital design, digital IC design. Analog layout
Okay.
is separate. So analog
Okay.
layout engineers will handle analog devices.
Okay.
Okay. So, ma'am, can you go to the slide? The previous slide, please, where all the modules are listed. Okay. So in this advanced physical design course, we will be having 6 modules. So in the 6 modules, the first module will be advanced digital electronics. So as we are going to design digital ICs, ma'am, I think you are sharing some other PPT. Can you please display the 6 modules? Yeah, so these are the 6 modules which we will be discussing in our physical design course. So the first module is advanced digital electronics. Under advanced digital electronics, we will be learning about combinational circuits, sequential circuits, and shift registers, flip-flops. So all of those derivatives of sequential circuits, we will be looking into that in detail. In the second module, RTL design using Verilog HTL. In this, how RTL design, but actually for this RTL design, there will be a separate set of engineers called as RTL engineers and verification engineers. So we will not be doing the design, but still it is important for us to know about RTL design, because the right immediate engineers who work before physical design engineers are RTL design engineers. So it is essential for us to understand what kind of work they do. Because if we are having any errors or if we are getting any bugs in the inputs that we receive from them, we have to work with RTL design team to fix it. Or sometimes if they are not available, we have to debug the code, and there will be a requirement for us to understand and clear the bugs in the code. So that is why we have included RTL design using Verilog HTL as module 2. In third module, ASIC flow. ASIC means application specific integrated circuit flow, which is the entire physical design flow. So physical design starts from a process called synthesis and ends in a process called sign-off. So I will explain all of this in detail in the upcoming slides. So what will happen from synthesis to sign-off? All of those detailed processes we will be discussing in module 3. In module 4, Linux and Tickle scripting. So Tickle is the hardware language that we will be using for physical design. For RT design, we will be using Tickle. Tickle means tool command language. Just like how we have some other programming languages like Python or Java, we have tool command language. So we will be discussing about the structure of Tickle, how to develop Tickle scripts for physical design. And Linux is an interactive terminal, so there is no need for us to go in detail of Linux, but we will be using basics of Linux to communicate with the EDA tools as in physical design tools. So we will understand the basics of Linux and the entire part of Tickle in module 4. In module 5, RTL to GDS flow. So again, the physical design flow with DFT insertion. So DFT insertion is one other topic, which I will explain later in the upcoming slides. And module 6 will be your final projects. And throughout these 6 modules, you will be having assignments also, weekly assignments and tests also you will be having in between. So for example, if we complete module 1, we will be having assignments and tests in that, and then we will proceed with module 2. So like that, it will proceed. Ma'am, can you go to the second slide? Okay, so in module 1, these are the topics that we will be discussing. Digital logic design, all the basic topics like Boolean algebra, Karnaugh maps, all of that, and all types of combinational logic circuits. Combinational logic circuits means your gates, and then sequential circuits, all the latches, flip-flops, types of flip-flops, how to derive one flip-flop from another flip-flop, all of those combinations of derivation of flip-flops, we will be discussing that. Shift registers, up down counters, so those type of counter designs also we will be discussing. Finite state machine, this is an important concept when it comes to RTL. So FSMs we will be discussing. Memories, again SRAMs, memory architecture, how is it formed, how an RTL is returned for a SRAM, all of that we'll see in that. And static timing analysis, this is the most important topic for physical design, so we will cover that. And CMOS logic design. Now CMOS has evolved. Now we were using when MOSFETs. So from MOSFETs, the industry has moved into another variation of transistors called as FinFETs. So we will be discussing the working and operation of a MOSFET and why we have moved from MOSFETs to FinFETs. So there were some shortcomings in MOSFETs, and those are called as short channel effects. So we will study those short channel effects and how these short channel effects are curbed in FinFETs, as in how we have overcome these short channel effects and how we have proceeded to FinFETs. So we will study that also in CMOS logic design. Ma'am, can you go to the next slide?
Yeah, just a minute. Another girl is going to share the screen.
Yeah, okay, fine. Okay, in the meantime, can you all type in the chat if you guys are final year students or if you have some experience or how you're trying to get into the VLSI industry from some other domain like IT or something like that. So can you please type in the chat so that we can know how diverse our group is. Okay, MTech students are there, final year students working on FPGA boards. Okay. Fourth year, sixth semester, just completed masters, looking for full-time jobs in VLSI industry. Okay.
Yeah, Christina, after this interaction, you can continue.
Okay.
Madhukta has shared the screen, okay?
Okay, fine. Third year students, good. Okay. Final year student, I have completed 32-bit adder RTL to GDS2. Very good. Okay. So mostly there are final year students and a few MTech students are there. Are there any experienced people in this chat who are looking to move into VLSI domain? Because, yeah, okay. Because anyways, we have to start from the scratch. So be it final year students or anybody who is looking to move into VLSI from another domain. Because for them alone, you have to go back and start reading your digital electronics, because at least third year and final year students will have a grip of it. So you guys must put in more efforts. Okay. Okay, fine. Then I will move to the PPT now. So this is module 2. I hope everybody can see the screen. So in module 2, we will be covering RTL design using Verilog HTL. So there will be an RTL design engineer who will be teaching you RTL. So all blocking and non-blocking assignments will be present, and you will be having lab sessions also for that. Introduction to the process of synthesis. So synthesis is the first process of physical design. And don't worry if you don't understand anything right now, because many terms which I'm talking about now might be new. So I have another upcoming slides where I have explained everything. So for now, we will proceed with the flow. All right. So coding RTL for synthesis. Okay. So as I said, synthesis is the very first step of physical design. Now, to start with the synthesis, we need the RTL part. So that will be explained in this coding RTL for synthesis part. Next is modeling of combinational circuits, latches, flip-flops, registers, counters. So for example, if you are going to use a multiplexer in your design, in your IC, in RTL, you will be using an if-else statement. If you are using a flip-flop in your IC, you will be using keywords like pause edge, neg edge. So like this, you will be able to model your combinational circuits and sequential circuits using the behavioral structures of your RTL. So what I gave is just an example. Next is counter design. So counter design, how to design a counter using an RTL. So that will also be discussed. And then RTL design for finite state machines and memories. Please keep in mind, memory architecture will be very important when we are dealing with RTL design. And then RTL design and verification for FIFO, RAM, and ROM. So yeah, memories again. Test bench concepts will also be discussed. Regular assignments and mock tests will also be given after each module is completed. And interview preparation for RTL will also be provided. So this is with respect to module 2. Okay, please go to the next slide. Okay, so this is the most important module of our entire course, ASIC flow. ASIC means application specific integrated circuit flow. So I will read through each point and then I will explain. Okay. So please look into the slide. The first one is specification. So this is what I was talking about. This is called system specification, where clients submit their specification to the VLSI domain experts, where they define the functionality, performance, and constraints of the IC, of the ASIC. So, for example, if we are going to develop an IC for a phone, the size of the ASIC must be very small, which should be able to fit in a phone. And if you're going to develop an IC for a laptop, considerably the size can be bigger. Now, this is called as constraint. Constraint of the IC means conditions, as in these are the conditions of the IC, and when we are doing our physical design for the IC, we should not go beyond these constraints. We have to adhere to these constraints. So this area is one such constraint. Next is frequency of the design. So if the client says the IC which is going to be designed must operate in 1 gigahertz, then what is the time period of that IC? If 1 gigahertz is the frequency, what is the time period? 1 nanosecond. So what does that mean? The data which our flip-flops are going to carry and propagate must not take more than 1 nanosecond. So that is again called a constraint, a timing constraint. We can call it like that. Okay, so like this, many constraints will be given by the client. So we have to make sure that our layout, which we are going to develop at the end of the physical design, must adhere to all of these constraints. So we will look into all of this in detail in the course. So what are the different types of constraints, how to deal if these constraints are getting violated, how a physical design engineer should fix it. So all of that in detail we will see in the course. Next is architecture design. So now we got the requirements from the client. Next is architecture design. So this architecture design will be done by the top level team of our VLSI domain, of whichever company you're going to work. Their top level team will do the architecture of the IC. Architecture of the IC means how many SRAMs must be there, how many ALU, arithmetic logic units, must be there, how many interface buses must be there, how many input ports, how many output ports, how many power ports. So all of this, designing all of this is called architectural design of the IC. So based on the specifications submitted by the client, architectural design will be done. And that will be done using hardware description languages like Verilog or VHDL or system Verilog, whatever it is. Okay. So that is all about architectural design. Next is RTL design. So in this RTL design, the functionality of the architecture which was developed will be written. So for example, in the architectural design, they have come to a conclusion that I need 4 SRAMs. Okay, 4 SRAMs with two, like, and the, okay, I will type this. So 256 cross 256. So this should be my SRAM size. So now the RTL team has to write a functionality or a coding for this SRAM. So sometimes the size will also differ. So depending upon the requirement, memory size, the size of the RAMs will differ. So like this, the RTL team has to write the programming for the architectures that were defined previously in the second step. The fourth step is verification. Verification means we will verify if the code that was written by the RTL engineers were correct or not. So all the debugging of the code will happen there. So what they will do, they will use some simulation tools where they will run the RTL which they have developed, and they will find if there are any errors or if there are any warnings which the design engineer should work on, or if the design has passed. So all of this information we will be getting when we are doing the RTL verification. Next is design for testability. So there are one other separate set of engineers called as DFT engineers. Again, DFT engineers are separate. Okay, we will not deal with them. We will be, DFT engineers will design some test patterns and they will give it to the physical design team. So we have to take those inputs and just implement them in our design. So that part alone, we have to work on it. So designing the test patterns will be done by DFT team. Taking those test patterns and implementing it on the IC will be done by PDT, physical design team. Okay. Next is synthesis. So from part 0.6 to 0.9 will come under physical design. So as I told previously, there will be a set of engineers who will be working, I told, right? So these are the set of engineers. So from 0.1 to 0.5 are the different set of engineers who work on the IC. The final and the last set of engineers who work on developing the IC layout is physical design engineers. And we will be studying from 0.6 to 0.9. Point 10 and 11 will go to manufacturing team. So we will develop the layout and give it to the manufacturing team. They will do the fabrication process based on the layout that we have submitted. Okay. So now I will explain what is point number 6. Point number 6 is called synthesis. So in the synthesis process, what we will do is, now we will have the RTL, right? So RTL design engineers, they have written the code, they have verified the code, and testing DFT patterns are also generated by the DFT team. So now in synthesis part, we will be generating one file called as gate level netlist. So I will read through that line. Translate the RTL description into a gate level netlist representing the ASIC using logic gates and components from a technology library. So this gate level netlist is the most important input for physical design. And this gate level netlist will be generated by a process called synthesis. How we are going to generate that netlist, what tools we are going to use, what inputs we are going to use. All of this we will be studying in detail in synthesis part. Okay. Now we have generated the gate level netlist. Synthesis is done. Now with this gate level netlist only, we will be entering physical design. So in physical design, we will be starting with a process called floor plan. So I will explain that in the upcoming slides. I will give an introduction of physical design now. So what is mentioned there? Place and route of the ASIC components on the silicon die, optimizing for performance, power, and area. So all of these processes we will be doing in physical design. Place means placement of the standard cells. Standard cells means our combinational cells and sequential cells. We will call them as standard cells. Okay. So we will place those cells on the layout, and route means giving electrical connections for these combinational and sequential cells. So that is called as routing. So placement and routing of the ASIC components we will be doing in physical design, and we will optimize them for performance, power, and area. So what is this performance, power, and area? This is called as PPA parameters. I will mention this again in the chat. So when you start reading more, or when you start the course, this PPA you will see in many of the places. You will see this PPA because this is the most important part. Now the agenda of a physical design engineer is two. First thing is to maintain the functionality of the IC, and second thing is to optimize the IC. I will type that as well. Functionality of IC, optimize the PPA of IC. So these are the two important agendas of a physical design engineer. So for example, I'll give you a simple example. There is a full adder. Okay, we all know what full adder is going to do. What is the function of a full adder? Now what I will do is I have a RTL coding for full adder. Now I have to implement this full adder functionality physically on an IC. So this part only I will be doing in physical design. So I have to make sure that this full ladder functionality must not change. So when I am doing part 6.6, 0.7, 0.8, and 0.9. So when I'm doing all these 4 processes one by one, none of these processes must not alter the functionality of a full ladder. Now, for example, I have a Boolean function y equal to a dot b. Okay, I'm just performing an AND operation for a and b. Now, after 0.8, which is timing analysis, if y equal to a dot b is changed to y equal to a plus b mistakenly by the tool, do you think it is right? Can we proceed with the design? Correct. So we cannot proceed with the design, right? We have to maintain the functionality of the IC. So that is the first main agenda for a physical design engineer. Functionality must be maintained because we are going to deal with millions of transistors and millions of operations are going to be handled by this particular IC. So if the tool which we are going to use for this physical design is going to alter the functionality, then there is no use, right? The entire design is completely fault. So the first thing is functionality of the IC must be maintained. Second thing is optimization of PPA, which is power, performance, and area. Power means, now for example, if the client requirement, if the client is saying my leakage power must not go beyond 0.2 milliwatt, we have to make sure that our design is not going to leak any power more than 0.2 milliwatt. And if they give some tolerance like plus or minus 5%, that must be our tolerance level. It should not go beyond that. That is one example for optimizing the power. All right. Second thing is performance. Performance means timing. So we discussed this 1 nanosecond example, right? So if the client is saying, I want my IC to operate in 1 gigahertz or 2 gigahertz, my design, which I am going to complete during physical design, must adhere to it. So the sequential cells which I'm using in this physical design must be able to launch the data and capture the data in that 1 nanosecond time period. If it is going to take 1.1 nanosecond or 1.3 nanosecond, again it is a failure. So that is called performance. Next is area. So area as in some 250 micrometers. So if this is the area specification given by the client, I have to design my IC in this area specification, not less than this, not more than this. So these are the 3 important standards. One is power, performance, and area. How we are going to do it, how we are going to optimize the design, all of that we will be seeing in point number 7. In physical design part, we will be seeing how to optimize this as well. Next is timing analysis. So in this, out of this power, performance, and area, the most important priority must be given to performance more than power and area. So that is called, so for that we will be following a separate method called as static timing analysis. So this, for doing the static timing analysis, we are having separate tools. Like we have tools like prime time and tempus. So we have tools like this to do this STA. So what we will do is we will run an entire timing analysis on the design that we have built, and we will check if the timing criteria or the constraints that were mentioned by the client is met or not. Ensure that all timing requirements are met, avoiding issues like setup and hold violations. So when we go into the static timing analysis concept, there we will see something called as setup time and hold time, and how we have to fix if the setup time is violated and hold time is violated. So we will be seeing how to fix them as well. So all of that part we will be seeing in timing analysis. So the details of the setup and hold time violations we will be discussing in the course. All right. Next is final verification. In final verification, performs extensive testing to verify that the fabricated ASIC meets all specifications and requirements. So in final verification, we will be dealing with something called as DRC and LVS checks. Again, I have added that in the chat as well. So DRC and LVS checks means DRC is called as design rule check and layout is called as layout versus schematic check. Details of this we will be seeing in the course, but for now to give you an idea about what final verification is, I've included it. So for this DRC, we have a separate rule deck, and for LBS, we have a separate rule deck. And we will be following this. We have to make sure that our design is adhering to those rule decks. If someone has asked a doubt, ma'am, what is the highest technology node using right now in the industry? Right now, 3 nanometer and 2 nanometer designs are being used. So I think Broadcom is using 3 nanometer and Intel is also using 3 and 2 nanometers. So okay, next I'll move to point number 10, which is manufacturing. Send the finalized design to a semiconductor foundry for fabrication. So we will be, so the process of, I will type this again in the chat, process of moving the GDS layout to the fabrication team is called as tape out. So tape out means we have successfully pushed the GDS layout from the design team to the manufacturing team. So that will happen after this tape out is being done. Manufacturing team will take the charge. So they will start manufacturing the IC and the semiconductor foundry will take care of this. Next is packaging and testing. So once the production of the IC is done, packaging and testing will be done on the IC and products will be delivered. So this is the entire life cycle of an IC, starting from system specifications to packaging and testing. And point number 10 and 11, they will be done by a set of engineers called as process engineers. Again, it is a different domain where they will work on the semiconductor foundries and they will conduct a series of tests on the IC that is being fabricated. So once the IC passes all those checks, packaging and testing will be done on those ICs. How the PD engineer is going to fix the area in PPA. Okay, so for this, we have many optimization techniques. So for now, if you're asking, we have multiple, we have cells with multiple areas. So we can change the cells with a lesser area and we can follow some optimization engines by the tool. So this part I will explain later. Once this webinar is over, I will come to this part. Because if I explain how area is going to be optimized now, I don't think everybody will be able to understand that. Can you go to the next slide? Can you move to the next slide? Yeah. So inputs of physical design. I will run through this slide. In detail we will study in the course, but since this is a demo session, I'll just give an example of what each of the file is. So these are the input files, all these 12 input files we will be receiving, and we will start our physical design with this input files. Okay. First one is called as gate level netlist, which we will be getting from the synthesis team. Okay. Next is the constraint files. It is called as SDC file. SDC file means synopsis design constraint. So synopsis came up with these with this input. So it is called as synopsis design constraints. And globally, it is called as this SDC file is only used. So they call it as standard design constraints also. So in this constraint files, all the timing constraints, power constraints, and area constraints that were specified by the client will be mentioned. So this constraint file will be generated by the top level team. So in our, for example, if we are going to design an IC, top level engineers or senior engineers will create this SDC file. So an entry level physical design engineer will not work on an SDC file. They will get this SDC file as an input. So as you gain experience, like 3 years or 5 years or 7 years, depending upon your expertise and talent, you can start designing this SDC file. Next is logical libraries, physical libraries, technology file, RC coefficient file. Now these 4 files from point 3 to point 6, we will be getting from IP vendors. IP vendors means, see, all the combinational cells and sequential cells that we are going to use in our design will be licensed, and we will be purchasing them from these IP vendors. So the gates and counters and memories that we are going to use, all of these are patented designs. So we will purchase them from these vendors and we will use them in our design. That is why they are licensed. Okay. So when we are getting these cells, this combinational and sequential cells from these vendors, they will give a set of files as inputs. Those files are these 4 files: logical file libraries, physical libraries, technology file, and RC coefficient file. Okay. So logical libraries and physical libraries are with respect to the combinational and sequential cells that we are going to use in our design. Technology file is with respect to the technology node that we are going to use in our design. So what is a technology node? Anybody has any idea what is a technology node? Yeah, the nanometer. What is this nanometer? So many were asking this doubts. What is this 3 nanometer, 5 nanometer? Yeah, I'll come to this. Anybody has any idea what is this 3 nanometer technology, 5 nanometer technology? It is what we say 3 nanometer. Okay. So
the number of chips presented in particular area or a feature size or a die.
No, not the number of chips.
It is the distance between the
number of
source and
transistors.
No, it is the
distance between source and drain.
Yeah, it is the distance between the source and drain of a MOSFET.
Like channel length, okay.
Channel length, exactly. So your channel length is called as technology node. So in industry terms, we will call it technology node. So if we are going to use a MOSFET where the distance between the source and drain is 3 nanometer, then we will call it as a 3 nanometer technology. If the distance between the source and drain is going to be 5 nanometer or 7 nanometer, we will call it as 5 nanometer technology or 7 nanometer technology. All right. So this technology file is with respect to this nanometer. So if we are going to use a 3 nanometer technology, all the rules with respect to this 3 nanometer technology will be present in this technology file. And if we are going to use a 5 nanometer technology, the rules will change. So these rules will change with respect to the technology node that we are going to use. So that is why this technology file is very important, and it is with respect to the technology node. Next is RC coefficient file. RC coefficient file means the resistance and capacitance values will be present in this RC coefficient file. So we will see this in detail, why we are going to use this file, where we will use this file. We'll see in detail later in the course. Next is another one file called as multi-mode multi-corner file. It is called as MMC file. Okay. So this point number 6 and 7, these files are going to help us to reduce the delay in our IC. Okay. So that how we are going to use this file, what are the contents of this file, we'll see later. But for now, you try to understand that RC coefficient file and MMC file we will be using in our design to reduce the delay of our design. Okay. Next is point number 8, which is called block partition file. So block partition file means, see, we have one IC and it is not like only one engineer will work on that IC. That entire IC will be divided into separate blocks. So we can categorize them into multiple blocks, like 5 blocks or 10 blocks, depending upon how much functionality is present in each block, depending upon how dense is the IC. For example, if one IC is going to have billions of transistors, only one engineer cannot work on that IC. It is very hard to close the timing and resolve the issues in that IC. So what they will do, they will partition the entire IC into blocks. So it is basically like cutting the IC into multiple blocks. And once physical design is done for each of the block, we will reintegrate all of the blocks together as one IC. That is called as block partition. Okay. So in physical design terms, so they will ask you, are you a block level engineer or a system on chip engineer? Block level engineer means you are working on a one block of an IC. SoC design engineer means that engineer will work on the entire IC. So when you're starting your career, you will start as a block level engineer. Based on your expertise and talent, you can move into SoC level engineer. So SoC level engineer means that engineer has a lot of experience and a lot of exposure with respect to physical design. That is why once they are able to handle an entire chip altogether, one entire SoC will be handled to that particular engineer. Okay. Next is IO pin location file. IO means input output location. So now we have our block. Now assume there is a rectangular block. Okay. In the rectangular block, where this input and output ports of this block will be present. That information will be present in this IO pin location file. So for example, if input ports are sitting on the top of the rectangular block, or on the bottom, or on the left or right, so all of this information will be present in the IO pin location file. Next is power plan script rule, power intent and switching activity. So all of these three files, so point number 10, 11 and 12, these three files are with respect to the power of the IC. How we are going to supply power, how we are going to manage the power, if there is any IR drop in the design, how we are going to fix it. So all of this information will be present in these three files. Okay, power plan, power intent and switching activity. So we will be studying in detail of all of these 12 files in the course. Can you move to the next slide? Okay. Next is floor plan. So as I said, before floor plan, we will be starting with synthesis. So in synthesis, we will generate the netlist, and netlist will be issued to the physical design engineers who start with floor plan. Now, sometimes synthesis will also be done by a physical design engineer, and then they will start with floor plan. Sometimes synthesis will be done by a separate engineer called synthesis engineer. So it depends, again, it depends on the requirement of the project and expertise of the engineer. So if one engineer is able to do synthesis and continue with floor plan as well, then that block details will be assigned to that engineer. Or if it is not possible, or also if there are some multiple blocks, there are some 30 to 40 blocks, one IC is segregated into 40 blocks, then we need 40 net lists for each of the block, right? So there will be some 5 or 6 engineers, synthesis engineers, who will take care of 10 blocks. 10 net lists each synthesis engineer will generate, and after generating the net list, they will push it to the physical design team. So like this, depending upon the requirement and also depending upon the functionality of the IC, this work will be segregated. But keep in mind that physical design starts from synthesis, and then only we will start with floor plan. So I'll explain what we will do in floor plan. Can you go to the next slide? Okay, so yeah, this one. So this is a schematic of a floor plan of one IC. Now in this floor plan, what all we will do is we will decide the height and width of the block. Next is, can you see these blue pointers on the edges of the block? The light blue ones, those are the input output ports. So the input and output ports of the block will always be on the edges of the block. Okay, so we will take the file which has the input output location, and we will load it inside the tool. And once we load it inside the tool, these input ports and output ports will sit on the edges of the block. So that is another one step which we will be doing in floor plan. Again, inside the block, you can see some orange and green blocks in the design. These are called as macros. Macros, again, we'll see in detail what is macro. There are two types of macros, hard macro, soft macro. There are many details. We will see that in detail in the course. So for now, you remember that we will be placing macros in the block during floor plan stage. And to place these macros in the block, we have separate set of design rules. Some 15 to 20 rules we have. So we need to follow those rules and place the macros in the block. So how we are going to place this block? Once these macros are placed in the block, how we are going to check if we have done it correctly or not? What checks we have to do once this floor plan is done? All of this we will be doing in floor plan. So this is the very first step. So once we get the gate level netlist from the synthesis team, we will proceed to floor plan. And in this floor plan stage, we will place the macros, and then we will run a series of checks on them. Once it is verified and it is passed, then we will move to another step called power plan. Can you go to the next slide? Okay. So in power plant stage, what we are going to do is basically we are going to give power connections to all the cells in our design. VDD and VSS connections, power and ground supply, we are going to establish for our block. That is what we are going to do in power plant. Okay, how we are going to do that? What calculations we have to do? So in the points you can see calculating number of power pins required. So how many power pins we need for our block? How many number of rings and stripes? So these rings and stripes means power rings and power stripes. So these power rings and power stripes only take the power supply to the interior part of the block. So the number of rings and then the width of the rings, what must be the width of the rings and stripes, how to calculate that, and how to establish these rings and stripes in the design, we will be seeing in power plan. Next is IR drop. So obviously we will see IR drop, right? Again, there are two types of IR drop, static IR drop, dynamic IR drop. If we see static IR drop, how we have to fix it. If we see dynamic IR drop, how we have to fix it. All of that in detail we will be seeing in power plan. So someone has asked why power plan in floor plan stage. I didn't understand your question. Can you elaborate your question? I didn't catch that. Power plan after which stage? After floor plan. Okay, so to fix IO drop, we will be adding some cells called as decap cells. So if once we add these decap cells, IO drop will be reduced in our design. Or we can also try to change the power architecture for our block. That is one other method of reducing the IR drop. Changing the power architecture means increasing the number of rings or increasing the width of the rings and stripes. That is called as changing the power architecture. So like that, we can reduce the IR drop. Why are VDD and ground rails wider in standard cells? Which one are you asking about? Can you unmute and ask your question?
Hello, ma'am. Usually in standard cell layouts, the VDD and ground rails are preferred to be wider metal layers. So, is there any specific reason for them to be wider, ma'am?
Wider for the standard cells?
No, ma'am. Standard cells.
Yeah. Wider. See, the metal layer width will increase as we go from the lowest metal layer to highest metal layer. So it is not necessarily wider. So for example, to give you a simple example, now assume if we are having some 9 metal layers in our design, the width of the metal layers will keep increasing as we go from M1 to M9. Now assume I am using M3 metal layer to connect my standard cell, and I'm seeing an IR drop in my design. So what I will try to do is, instead of using M3, so this is one of the fix. So instead of using 1.3, I will reroute and I will use M4 to connect my VDD and VSS of that particular standard cell. So why? Because as the width of the as the width of the metal layers increase, IR drop will reduce. And we will face one other issue called as electron migration. So as the width increases, these power issues will be reducing. So that is why we will be using higher metal layers if we are seeing IR drop issues and electron migration issues.
Okay,
So
ma'am.
to answer your question, to fix these issues that we are seeing in power plant, we will be using wider metal layers.
Yes, ma'am. Understood. Thank you.
Okay. How to decide the width of the stripes? So for this, we will be taking the information from, can you please go to the input slide, PD input slide? Okay, so if you can see point number 12 and 11, power intent and switching activity. So in this files, we will be having different types of cells. And in this file, we'll be having the switching activity of the cells. So based on the switching activity of the cell, based on the power requirement of our block and the current rating of our metal layers, we will be using certain formulas to come up with the width of these stripes. So this width of these stripes will differ for each block. So if you want the formula, I can share it in the group. Like after this demo session, I can share it in that WhatsApp group. How to decide how many stripes are required? Again, that depends on the requirement of our design. How many power pins, how many rails, how many straps, everything depends on how many standard cells are there in our design, how dense is the logic, what is the power requirement of these logic. So based on this only, we will be able to decide. Static and dynamic IR drops to fix any different methods for those, or same process can be used for both? No. For static IR drop, we have separate fixes, and for dynamic IR drop, we have separate fixes. For static IR drop, we will be using multiple threshold voltage cells to reduce the static IR drop, and for dynamic IR drop, we will be using decap cells. Decap cells means decapacitor cells we will be using to reduce the dynamic IR drop. Can you go to the next slide? Okay, next is placement. So in this placement stage, okay, next is placement stage. So in this placement stage, what we will do is we will place all the standard cells of our design. So standard cells means all the combinational and the logical cells of our design. So how we will be using the Innovus tool. If we are going to use Cadence tools, we will use Innovus. Or if we are going to use Synopsys tools, we will be using ICC2 or Fusion Compiler to do this physical design placement and routing, and we will be placing the standard cells. So in this placement process, it is very wide, but to characterize it for now, we can divide it into two steps. One is called course placement, another one is called legalization. Course placement means assume course placement as a rough placement that you do, and in legalization, we will do the detailed placement of the standard cells. So how to do that? We will be discussing that during the placement stage. Can you go to the next slide? Yeah. So can you see all those green, orange, and gray boxes inside the block? Those are called as standard cells. So these blue ones, which are big, are the macros, and these macros, we will be placing them in the floor plan stage. And this standard cells, we will be placing them during the placement stage. Okay, so this is what we will be doing during the placement stage of physical design. Next slide, please. Okay, next is clock tree synthesis. CTS means clock tree synthesis. So in clock tree synthesis, what we will be doing is we will be establishing clock signals for all the flip-flops of our design. So we will be using registers, right? Flip-flops in our design, and flip-flops are clock enabled. So we will be issuing clock signals to all of these flip-flops in the design. How to do it, we will be seeing in detail in CTS stage. So we will call this CTS as clock tree building, and there are multiple types of clock tree. How to build a clock tree for a design, all of that we will be seeing during CTS stage. Can you go to the next slide?
Hello, ma'am.
Yeah.
Is the frequency of this clock tree based on the setup and hold time of the flip-flops?
Yes.
Okay.
Yeah. Next is routing. So this is the final design stage of routing. So after routing, everything that we are going to do is only the testing and checking part, like timing analysis, final verification. All of these are the checks that we are going to do on our design. Routing is the final stage where we are completing the design. So the design part is over by routing. And in routing, what we will do is we will do something called as establishing signal connections. So now we have placed all the design, all the ASIC components. We have placed the input output ports, we have placed the macros, we have placed the standard cells, all the combinational and sequential cells we have placed. Now what is the final stage? We have to give routing, electrical connections we have to give to all of these elements in the block. That is what we will do in routing. So again, there are 3 stages of routing. First one is global routing. Next, we will do track assignment. Third is detailed routing. So how each of these stage will work, what we will be doing, what commands we will do, what scripts we have to run, everything we'll see during routing stage. Can you move to the next slide? So this is an example of global routing and detailed routing. In global routing, you can see all of the signal connections are present for all of the standard cells, but it is not regular. In detailed routing, you can see a detailed and a crisp connection that is established for all the standard cells in the design. So this is just a schematic of how the global routing and detailed routing will look. Okay, please give me 2 minutes. I'll be right back. Okay. Am I audible now?
Yes, ma'am.
Shall I move to the next slide? Okay, yeah, thank you. So, what can you go to the previous slide? Did we discuss that routing diagram? Yeah, okay. Next slide, please. Yeah, so this is STA, which is static timing analysis. So as I said, the design part is over. Hereafter, everything is the analysis, verification, and fixing part. All right. So STA is called as static timing analysis, which we will be doing for our block to validate the timing performance of the design. So as I said, if our design is going to work in 1 nanosecond, we have to make sure that all the timing paths in our design is going to use 1 nanosecond to transfer the data. So to ensure this, we will be doing this check called as static timing analysis. And to do this static timing analysis, we have separate tools. So the tools which we do for physical design are different, and the tools which we are going to use for static timing analysis is different. So I will mention the tools in the chat. So Innovus, ICC2, Fusion Compiler. These are the PD tools. Okay, for STA, for static timing analysis, we have Tempus and Prime Time. And for final verification, next we have Caliber, PV and IC validator. So the tools which we will be using. This depends on the company. Based on what licenses they use, we will be using the tools for each of these processes. So for static timing analysis, we will be using Prime Time tool and Tempus tool. Both are by different operators, but the operation and the analysis part, everything will be the same. It is just that we are using a different license, from a different vendor. That's all. So in this static timing analysis, can you go to the next slide? Can you go to the next slide, please? There will be a static timing analysis diagram. Can you go to that? Yeah. So these are called as timing paths. So you can see path 1, path 2, path 3, and path 4, right? These are called as 4 different timing paths. So timing paths means paths which carry data from one point to another point. Those are called as timing paths. So there are 4 types of timing paths, and the first type is path 1. So path 1 is the timing path from an input port to a flip-flop. So this A and clock, the ports are called as ports. So this is the symbol for input or output port or clock ports. So any input ports or output ports or clock ports that you're going to see in your design will have this symbol. So this path 1 is from input port A to the D pin of the first flip-flop. That is path 1. Path 2 is from the first flip-flop to the next flip-flop. That is path 2. Path 3 is from the last flip-flop to the output port of the block. So now assume you are having a block and there are 2 flip-flops inside that block. and there is one input port for that block, one clock port for that block, and one output port for that block. So likewise, there will be like this, there will be multiple timing ports, like thousands of input paths will be there, output paths will be there, flip-flop to flip-flop or register to register paths, multiple paths will be there. This is just one example, one representation of each of the path. And path 4 is, you can see the path 4 in the below part. So it goes straight away from the input port A to the output port Z. So these are the 4 types of timing paths. So I will type this as well. So into reg, this is how we call it. Reg means register, flip-flop, okay? Reg to reg. Reg to out and into out. So these are the 4 types of timing paths. And in static timing analysis, what we will do is we will analyze each set of these paths separately, and we will check if it is adhering to all of the timing constraints that are mentioned for our block. Now, the logic that you're seeing inside all those orange clouds are the combinational cells, which are present in that particular path. So combinational cells means what? Your logic gates, buffers, inverters, all of this comes under logic. So if they call it as logic, it simply means the combinational cells that is present between those paths. So in STA, this is what we will do. So we have many STA checks. We have setup violation checks, hold violation checks, recovery time checks, removal time checks, and then min period checks, clock pulse width violation checks. So like this, we have multiple checks, and we have to check if all of these paths are adherent to all of these checks, if it is passing or failing. If it is failing, we will do one more round of STA. If it is still failing, we have to redo our design. Again, we have to redo our design. And then once again, we have to go to STA. We have to check if it is passing or failing. And then we will move to final verification. So once static timing analysis is done and timing is closed, then we will do final verification. So there's a question, how STA can be done for multi-cycle paths. So first I'll explain what is a multi-cycle path for the others. Multi-cycle paths means paths that require more than one clock cycle for the data transfer to happen. Now in this diagram, if you can see in path 2, the data is getting transferred from the first flip-flop to the second flip-flop in 1 nanosecond. So if 1 nanosecond is the clock period, it is called as single cycle path. If it is, if this, I will type that again. 1 clock period means single cycle path. If the data require more than 1 clock period or 1 clock cycle, you can call it as a multi-cycle path. So if the data requires 2 nanoseconds or 3 nanoseconds to transfer the first flip-flop to the second flip-flop, we will call it as a multi-cycle path. So the question is how STA can be done for multi-cycle paths. So if we are going to use multi-cycle paths in our design, we will mention in the script that these paths are going to be multi-cycle paths. So there is a command for that. So set underscore multi-cycle path. So using this command, you have to mention which path is a multi-cycle path. So if you mention that these set of paths are multi-cycle paths, the STA tool will do the timing checks for them accordingly. Is it clear? Okay. Please go to the next slide. Okay. Next is called as sign off. So sign off is where we will be doing something called as ECO cycle. ECO cycles means engineering change orders. So in the sign off stage, what we will do, timing closure, design closure, we will be doing. So inside what we will be doing is, see, as we start the design from floor plan, power plan, placement, CTS, routing, then what will happen is after every stage of this physical design, we will be doing some checks. So once we complete floor plan, we will do some checks. Once we complete power plan, we'll do some checks. Once we complete placement, we'll do some checks. So likewise, after every process, we will do some checks and then we will proceed with the design. In sign off stage, what will happen is, if, for example, in placement stage, you missed out, okay, you saw a bug and you missed to fix it. In sign off stage, you can go back and fix it. That is why it is called as engineering change order. Now, can you go to that module 3 slide, please? No, not this. Where the ASIC flow, yeah. So this is the order. Now, if you see from point number 6 to 9, so this is what physical design is. This is the part of physical design, and this order must not be changed. So it is it is one only when synthesis is done we can do physical design. It is not like it's not like you can go from physical design to synthesis. So once synthesis is done, only then you can start with floor plan. Once floor plan is done, only then you can proceed to power plan. But in sign off, what advantage we have is, even if we see a bug which was missed to fix during placement stage, and still if we proceeded to routing, which is the final design stage, you can still go back and fix that bug alone. That is why it is called as engineering change order. You can change the order of the flow and you can fix the bug. And this in this sign off, only fixing will be done. It is not like you can redo the entire design during sign off, only fixing you can do. So how to do these engineering change order? What is the procedure to do this ECO cycles? We will be seeing in detail during sign off check. Can you come back to final verification stage? Yes. So next is physical checks. Now for checking timing, we are doing static timing analysis. To do physical checks, which are called as, there are two types of physical checks. One is called as DRC check and LVS check. DRC check means design rule checking, and LVS checks means layout versus schematic checking. So there are two types of checks which we have to do separately, and these types of checks are called as physical checks. Now again, to do this physical checks, we have a separate tool called Caliber PV, our IC validator also. So in using this, we will be able to check if our design is adhering to the design rule constraints that are given and the layout constraints that are also mentioned for our block. We'll be seeing in detail what this DRC and LVS is during the course. But for now, please understand that DRC checks and LVS checks are physical checks, and there are separate tools to do these checks. Those tools are IC validator and Caliber PV. So these are the two tools which we will be using to do these physical checks. Next slide, please. Okay. Next is issues in physical design. So when we are doing our design, when we are starting from floor plan, we will be facing some issues throughout the entire process. So to fix those issues, first we need to understand what are those issues. So those issues also we will be discussing in the course. So the first issue is this the first slide or first slide of issues? Can you go to that electron migration? Next slide after this. Yeah, I'm getting some questions about setup and hold. So please wait once this issues is the final stage. So once this is discussed, I will explain that. So the first issue which we will be seeing is electron migration. Electron migration means, see, assume there is a metal wire and through that metal wire, we are passing current. Now, every metal wire will have its own tolerance. Like only this much amount of current density is allowable through that metal wire. So if this value is being violated, if high current density is being flown through this metal wire will start to rupture. That process is called as electron migration. So this electron migration you will see during during power plant stage. So once we establish the VDD connections, we will start seeing this electron migrations. If the metal layers which we are using in our design is not able to withstand the heat generated by the high current density that is flowing through that metal wire, then we will see, then this electron migration process will happen. And what will basically happen because of this electron migration is the metal wire will either short within the next wire or it will open. So basically the metal wire will break because of this electron migration. Now we have to fix this electron migration. So this also caliber PV tool we will be using. Okay, that is all about electron migration. Next is latch-up effect. Latch-up effect means the MOSFET that the second diagram will explain latch-up. So what is the process of latch-up means? Inside a MOSFET transistor itself, a parasitic transistance effect will be getting created because of the multiple P and N regions that are being developed on the same substrate. So it is basically like there is one main transistor and there is one more another transistor which is getting created inside that transistor because of the multiple P and N regions which are close to each other. So because of this parasitic transistor which is getting formed inside, current will start flowing internally inside the transistor, inside the MOSFET. And because of that, the MOSFET itself might break or it might become faulty. That is called as latch-up. Again, details of latch-up we'll see in the course. How to fix latch-up, what measures we have to take to fix latch-up, we will see. Can you please go to the next slide? Okay, so here we will see two other issues, which is IR drop and signal integrity and crosstalk effect. IR drop is a very common term which you must have come across this during your study itself. So what is IR drop? So if a standard cell or if a logic gate is requiring 1 volt, so we will be using the wire connection to take this 1 volt from the VDD port. So when the current is being transferred from this VDD port to the standard cell, because of the metal zone resistance, we will see some IR drop. So instead of this 1 volt, which is required for the standard cell, we might see some reduction in the voltage, like 0.9 volt or 0.8 volt only will reach the standard cell. So because of this, what will happen? The standard cell will not turn on, as it requires 1 volt to turn it on. We are getting only 0.9 or 0.8. So the standard cell will not turn on, which will lead to functionality failure of the design. So we have to identify this IR drop and we have to fix it. Okay. Next is signal integrity and crosstalk effect. So for the signal integrity and crosstalk effect, please look into the second diagram where there are two nets. Nets means metal wires. So there is one red color wire and yellow color wire. Okay. So what is the basic concept of this crosstalk effect is, if there are two nets or two metal wires carrying signals which are placed close to each other, a coupling capacitance effect will get created between those two wires, and one uh, a signal in one net might get affected because of the signal in the other net, because of which functional failures and also timing violations might happen in our design. So that is called as crosstalk effect. So to avoid this crosstalk effect, again we have some measures. So for example, so if you run this command report noise, the crosstalk which we are seeing in our design will be we will be getting reports of this crosstalk, how much crosstalk we are seeing in our design. So based on this reports, we have to fix the crosstalk. So how to fix it, all of that also we will study in the course. So what is the difference between crosstalk noise and crosstalk delay? Okay, so to explain this, so there are two nets. So you can see aggressor and victim. So this red net is called as aggressor because it affects the data in this in the second net which is below it. That is why it is called as the aggressor net, and the net below it is called as victim net because the data or the signal in this second net which is below is only getting affected because of the net which is above it. That is why it is called as victim net. Now, this is called as crosstalk. Data getting affected because of one net. Okay. And there are two types of crosstalk. One is called as crosstalk noise and crosstalk delay. So crosstalk noise means if the data in aggressor net is switching. So if the aggressor net is switching, I will type it out. And victim net is constant. Next case is aggressor net data also switching, and victim net data is also switching. So the first case is called as noise. The second case is called as delay, crosstalk delay. So I have mentioned that in the chat. So for example, if the aggressor net is carrying some data, data stream like 0, 1, 1, 0, something like this. So there is constant switching in the aggressor net. In the victim net, the data is constant, like a constant 0 or constant 1. In this case, if the aggressor net is affecting the victim net, an issue happens which is called as crosstalk noise. Second case is if the aggressor net data is also switching, like 0, 1, 1, 0, or some pattern of data is flowing in the aggressor net, and in the victim net also some switching is happening, then we will see an issue called as crosstalk delay in between the nets. So this is the difference between crosstalk noise and delay. Is it clear? Okay. So this is all about this entire the all these these are the 6 modules. So the 6th module will be the projects. So that could be either 28 nanometer and for 45 nanometer. That depends upon the project that I'm for now I'm not sure which project node Prashanti is getting for us. So, but it should be either 28 nanometer or 45 nanometer. In this technology node only, we'll be doing the projects. So these are the 6 modules. So this is how the entire structure of this course will be. Any doubts? We can discuss now. So somebody was asking about where Tickle is used and how. So Tickle is the scripting language that we will be using to load the commands to the EDA tools. So in Innovus, so all the tools that we discussed, right? Innovus, Tempus, PT. So to all of these tools, we will be giving commands as inputs. And these commands will be written in Tickle format. Can you please explain what will happen if the setup time is not met as per required? So if the setup time is not met, we will see a setup violation, and that data path will be called as a timing violated data path, which means that path is requiring is more than the clock period, and more delay is being seen in the timing path. So that is the meaning of that. So if the time period is 1 nanosecond, and if there is a setup violation there, it means that the data is taking more than 1 nanosecond for the data transfer between the launch flip-flop and the capture flip-flop. So if the clock period is 1 nanosecond, and if a data path is taking 1.2 nanosecond for the actual transfer, then it means that the setup the setup violation in this example is 0.2 nanosecond. So now after identifying this, we have to fix. So there are multiple methods to fix setup timing violation. So we have to follow those methods and fix so that can possible IEEE paper. Sorry, I'm not able to catch your question. Which we can publish for. Okay, what next after 1 nanometer technology? Good question. So now 1.8 nanometer and 1.6 nanometer is under research. So now the next research that is happening is something called as chiplets. So first we moved from MOSFETs, then we move to FinFETs, then we are moving to 3D-IC technology, and then we are moving to chiplets. So less than 1 nanometer, if requirement, if we are going to see that level of expertise in our design, then we can use 3D-IC technology and chiplets to fulfill the requirement. So now by using FinFETs, we have reached 1.8 to 1.6 nanometers. So maybe by using 3D-IC technology and chiplets, we can reach that 1 nanometer technology also. Any other doubts? Yeah. During ECO process, how to reduce duplication of input clock gating cells and save clock gating buffer area and power. duplication of input clock gating cells. Can you explain that? Duplication as in you are asking if same number of clock cells will be clock gating cells will be created for the same timing path. Are you asking like that? See, clock gating. So since you're asking this question, I believe you know what is the meaning of a clock gating cell. So in one timing path, we will be having a fix, like for example, in one timing path with respect to one clock, these number of clock gating cells must be added for each timing path. So this information will be present in a file called a CTS spec file, which we will be using during the CTS stage. So duplication of clock gating usually doesn't happen. So it is not like duplication doesn't happen. Maybe clock gating cells might not be inserted in this in one timing path, and we can go back and insert it. Duplication of clock gating, mostly it doesn't happen. Or data doesn't remain stable. What will happen if the data doesn't remain stable before the clock edge? Or data doesn't remain stable after the clock edge. So yeah, that is the setup violation. If the data is not stable before the active edge of the clock, that is when setup violation happens. And if data doesn't remain stable after the active edge of the clock, hold violation happens. Metastability state means output will not remain in one state. It will keep toggling. 0 and 1, 1, 0, like this, it will keep toggling. It will not remain in the same state. For the same input, you will be getting different outputs at different times. That is metastability state. How does Tickle Perl scripting differ? Okay. So I have not used Perl scripting. So maybe I have to look into this question. How does Tickle Perl scripting differ? Okay, I have to look into this. So I will look into that and then I will add in the chat in the WhatsApp group. I will answer your question. Because so far I have used only Tickle scripting and I have not used Perl scripting. So I don't think me answering at this point will be right. What are the major changes need to be observed to go to lower nodes? Can you please elaborate on that? What are the major changes? Can you please explain this? What is the level sensitive latch? So positive level, so we have two types of latches, like positive level sensitive latch and negative level sensitive latch. So just like how we have a positive edge triggered flip-flop and a negative edge triggered flip-flop, we have multiple positive and negative levels, right, in the clock period. So if the latch is going to turn on and the data is going to be latched for the positive level, it is called a positive level sensitive latch. If the data is going to be latched for a negative level, and if it is going to be transparent for the positive level, it is a negative level sensitive latch. For power pin, higher metal is good for design or not. For power pin, we will be using only higher metal layers because the IR drops will be more in the power pins. So we will be using higher metal layers only, because as I discussed earlier, the width of the metal layers will increase as we go from the metal layer one, from the lowest metal layer to the highest metal layer. So we will be using higher metal layers only for power pins, because as the width of the metal layers increase, the ion drop and electron migration issues which we will see will be less in higher metal layers. So obviously for power pins, we will be using higher metal layers only. From 5 nanometer to 3 nanometer, what are the advantages? So first is we will be able to accommodate more number of ICs, more number of transistors on the same area, because the size reduction of the entire transistor is happening, right? So more number of transistors you can accommodate on the same area, and also by this multiple applications you can integrate on the same IC. That is the advantage. See, because why are we calling this as an SoC design? System on chip, which means multiple systems or multiple applications can be run on a single IC. So if a single IC needs to run multiple applications, it needs millions and billions of transistors. So if we are going to accommodate more number of transistors in one area, multiple applications we can run with the use of those transistors. So that is the main agenda. That is why scaling of these transistors happen, so that multiple applications can be integrated on a single IC. NM technology. Mahesh, I'm not able to understand your question. NM technology. What do you, are you asking? What is meant by nanometer technology? Yeah. So it is the distance between the source and the drain. The channel length, I will type this. Channel length is your technology node. So the distance between the source and drain is your channel length, and that is called technology node. In PD flow, do we work only at the gate level, or do we also get into the transistor level of the design? No, transistor level of the design, that is done by analog layout engineers. We will not work in transistor level. What is the edge numbers for the latch-based timing analysis? Why do we have to go into edge calculation for latch? Because we don't use the edges, right? Latches are enabled by the levels. Or can you reframe your question? Madhavan, what is the edge numbers for the latch-based timing analysis? Can you explain that? Sweta Shri, any power effects of, can you again please explain that question? AI will impact on VLSI domain because nowadays more people suffer in software. Okay. See, AI will impact as in, see the tools that we are using, right? Innovus tool, Caliber PV, Prime Time, Tempest. So all of these tool enhancements only can happen because of AI. So by using AI in VLSI domain, by using AI for chip design, the time will be reduced, and the requirement of if 3 engineers or 4 engineers require 5 hours to do to complete one process, by the use of AI in the EDA tools, the time will reduce, and the number of engineers might reduce from 4 to 3. So it is not like AI is going to replace us and AI is going to do the chip design. It is not possible, at least for now, because AI is used only to enhance the correctness and the consistency of the EDA tools that we are going to use. So impact, if you're going to ask me, maybe down the line, more talented engineers only will be required, because as AI is enhancing the tools, more knowledgeable engineers only will be required. So I think that will be the impact. Maybe the interview process that is going to be conducted by the service level companies and the product level companies, that only will be stringent, because They need a lot of engineers who have a lot of talent and expertise. So I think that will be the impact, where getting into the domain will be more challenging. But replacing engineers, that is not possible. How is automation useful in PD flow? Okay, so automation, so for example, if I want to run my design and I want to see how my timing is responding to the issues. So for example, I'm going to do some timing checks and power and area checks on my design. So I will do an automation flow, and with that flow, the entire design will be automatically done by the tool, and it will give me a report of the timing of power and area. So by doing an automated flow, I can get an estimate of how my design is going to respond with respect to power, performance, and area. So by doing that, I'll be able to understand that, okay, this is an estimate of errors that I'm going to see in my design. And with respect to that, our automated flow, if I start the manual flow, then fixing of the timing violations will be much easier. So that is where automated flow will be helpful. Okay. Like, what is the number of levels for the latch timing analysis? 1, 2, 3, 4. What is the number? Number of levels for I'm still not getting your question. So do you mean to ask in which level we are going to do the setup and just like how we do the setup and hold time for flip-flop, in which level we are going to do this timing analysis for latch? Is that your question? Okay, so it depends on how many latches. Okay, just a second. So these latches we will be inserting in a flip-flop. Can we use latches? Yes, we can use latches in our design. So if there are two flip-flops, one is the launch flip-flop and the capture flip-flop, and if I have used a latch in between. So if I'm going to use a positive edge triggered flip-flop, I have to use a negative level triggered latch, so that at the negative level of the clock of the first clock period, setup and hold time for the latch will be checked. So it is not like, so it is at the negative level of the first clock period if I'm going to use a positive edge triggered flip-flop. So that is how we will be doing the timing analysis for the latch. Negative level of the first, okay, I will type it. Negative level of the first clock cycle after launch flip-flop. We will do the latch timing analysis. Okay. In the synthesis time, sometimes the time come negative, and how we solve it? When clock period is 10, waveform is 5. How to solve this frequency when generating the netlist? Sometimes time comes negative means you mean to say the and how we solve it. Okay, we'll be adding buffers inverters to fix timing violations. We can add or remove buffers. used to invert use multiple types of cells like LVT, HVT, and SVT cells. Pipeline the design, retime the design, multiple cells. So these are, so I have mentioned a few of the timing fixes. So we can these methods to fix the timing violations. How the set and hold violations can be handled if all the violations occur. Yeah, so for this question, I mean, it is the same question. The previous person asked the same. I have mentioned the fixes, timing fixes in the chat. You can check that. Will the slides and recording be shared after the meet? Yes, it will be. Can we use latches? Yes, we will be using latches in the design. CAD tools means which tools? We don't call them CAD tools. We call them EDA tools, which are called as electronic design automation tools. And the most widely used tools are from Synopsys and Cadence. Okay, so Synopsys tools are DC, Design Compiler for Synthesis, ICC2 for PD, Fusion Compiler. Fusion Compiler will do synthesis and PD together. Okay. And then prime time for STA. Next is Cadence tools. So the Cadence tools are Genus for synthesis, Innovus for PD, and then Tempus for timing, STA part. So these are the tools available in the industry and the most predominantly used tools. Next is how to write ECOs. So the tools will generate the ECOs. We don't write the ECOs manually. Tools will generate the ECOs. So Tempus and Primetime will generate the ECOs. So if some parts are not fixed in ECO, then we will manually write the ECOs for some timing parts alone. So to give you some examples of ECO commands, add repeater, insert buffer, ECO change cell. So these are some of the ECO commands. Where do we use Virtuoso and Power Compiler from Cadence and Synopsys? So this we will be using to fix IR issues, IR drop and EM issues. Then we will be using this these tools. And also if we are running a low power design. So sometimes the clients will come with specific specifications like, I don't care about the timing or area, but the power which is incurred in my design must be very low. So those designs are called as low power designs, and separate extra set of inputs will be given for this low power design called as UPF file. So this again, we will see all of this in detail. So all of these files we will be using to do this low power design. So when we have to do power optimization, then we will be using these tools. Any other questions? Then or else we will safe means switching activity interchange format. So that is the expansion. Switching activity means how frequently the data, a cell is switching with respect to the clock. Activity information will be present in the safe file. Activity information means how frequently the data is switching in that cell. So if you take a clock cell, clock will be very actively switching because it will be generating clock signals continuously. So it is a continuously switching cell compared to logic gates or buffers. So the activity value for the clock will be more compared to logic gates and other buffers or inverters or other sequential cells. So that is called as, how can we derive safe from VCD file? How can we derive? So I believe there are separate tools for this. So this one I'm not sure for now because this will be handled separately by power optimization engineers. So this one I'm not sure for now. Maybe I can check and let you know. Why hold checks are done at 0 clock cycle? Because see, hold check is done at the same clock cycle, at the same clock edge, is because the data. So, for example, 0 is getting transferred to 1 flip flop. So after this 0, 1 is getting transferred. Now the 0, which is now present in this flip flop, will be it must be stable for some time before it is getting transferred to the next flip flop. So that is why it is checked if it is stable at the same edge, because this data must be stable in the same flip flop before it is getting transferred. So that is why it is checked at the same clock cycle. If we are going to do the whole check in the next clock cycle, 0 will be missed out, 1 will be only checked. So the present data will be missed out. That is why we are using the same edge check for whole check. So to check the data present in the flip flop, we do same edge whole check. Because flip flops are 1-bit registers, right? So you cannot save more than 1 at a time during one clock cycle. So if you have a series of data like 0, 1, 1, 0, first for the first clock cycle, 0 will come, then 1, then next 1 will come, then 0 will come. So in the next clock cycle, 1 will come. So now I'm going to do a whole check for 0. I'm going to do a whole check for 0. For the first 0, okay, the LSB. In the next clock cycle, what must happen? The next data will come into the flip flop. So the next data is 1. So in the next clock cycle, the next data 1 will come to this flip flop. So this operation only will happen during the next in the next clock cycle. So if that is why I have to do the whole check in the same clock cycle. if I'm going to do the hold check in the next clock cycle, this 0 will be missed out. And 1, it is like I'm doing hold check for the next. That is why hold check is done at the same edge, at the same clock edge. Why setup check at next clock cycle? Because see, now this data is going to get transferred to another flip-flop, and it must be stable before the next active edge of the clock. Now the next clock cycle or the next clock pulse is going to carry this data. So that is why the data must be stable before the active next clock edge. So before the next active clock edge itself, the data must go and it must be stable for the clock to carry it to the next flip-flop. See, setup check is done with respect to the launch clock. Is launch clock edge, and hold check is done with respect to the clock cycle of the capture flip-flop. I think now you can get a clear picture. Setup check is done with respect to the launch flop clock. Sorry, setup is done with respect to the capture flop clock. I will edit it. What about schedule and class timings? I think Prashanti will discuss regarding this. I'm not sure because I think she is planning either if it is going to be a weekday or weekend session. So she can explain about that part. Okay, so I will go to module 4, Linux and Tickle scripting. So in this module 4, we will see fundamentals of Tickle scripting. In fundamentals of Tickle scripting, we will cover data types, operator types of operators, types of loops, types of conditions. So we have different types of loop breaking statements like switch and continue and break. And then we have some switch statements, for else statements, for each statements, and then we have procedures. So like this, we have different fundamentals, so that we will be covering. And then Tickle in EDA tools. Tickle in EDA tools means how Tickle scripting is used for physical design, that part. Automating placement and routing tasks. So to do an automatic placement and routing task, how to do a Tickle scripting. To do a design rule check, how to do a Tickle scripting. So like this, we will see some real-time applications, and lab access will also be provided for this module. Next is Linux. So we will be using the Linux terminal to make use of our EDA tools. So there is no need for us to go in detail of Linux, but just to how to operate the Linux terminal, how to play around the directories, how to move the directories, rename the directories, like that basic commands of Linux we will see. Next slide. You put it. RTL to GDS flow with DFT insertion. So this is again the ASIC flow only, but with DFT insertion we will see. So this DFT insertion is nothing but inserting test patterns in the design. So how this test patterns will be inserted. This test pattern generation we will not do. That will be done by DFT engineers. So they'll generate this test patterns and they will give it to us. So it is like one of the input for physical design. We will insert this DFT in our design and we will run a design flow check on this netlist with the DFT. So in that we will be discussing about scan chain design and insertion of scan chain design, boundary scan, JTAG basics. So again, this is just the basics, because when a test pattern is given to a PD engineer, we need to understand what is happening in that. So for that, we have to study about boundary scan techniques and BIS techniques. So how these techniques are then, how these test patterns are going to affect the design, only that part is required for us. How to generate, that will be done by a separate set of engineers. So how DFT insertions affect our design, that portion of DFT insertion alone we will be covering in module 5. Yeah, module 6 will be your final projects. So as I said, either it will be in 45 nm or 28 nm. So one full synthesis to sign off, we will be doing in the final project. So that is all about today's demo session. In this demo session, we have covered and of the domain and what are all the top physical design, like the inputs of physical design, and then every stage of physical design, which is synthesis, floor plan, power plan, placement, CTS, routing, and sign off. And then finally, static timing analysis, physical verification, which will involve DRC and LVS checks, and then the final project along with tickle scripting. So this will, all of these topics we will be covering in our advanced PD course. Class timings, yeah, Prashanti ma'am, she will let you know about that. If I don't know if she's in the call, maybe she can discuss about it now. Yeah, I will text her. I don't think she is in the call right now. Maybe after the end of this class, you can ask about the timings in the WhatsApp group. She will be explaining. What kind of topics to be read for DFT? For DFT, S pattern generation, you can learn. Impact of DFT on design, on physical design. You can go through these topics. Tools for DFT, again, since we are not generating DFT, we will not be using any tools. So only DFT scripts we will be using in the tool, in the Innovus tool. Sorry, thank you for that. RC abstraction, can you please explain? Abstraction or extraction, you're asking? See, RC extraction, yeah. So RC extraction we will be using to calculate the net delays. Calculate the net delays. So this there is a file called as RC coefficient file, which is one of the input file.
Input file.
So this file will have the resistance and capacitance values as per the net length. So once we use this RC coefficient file in our design, we will be able to get an estimate of the net delays in our design. So the delay of our entire block will be because of cell delay and net delay. So this net delay value we can get using this RC extraction. RC coefficient file. RC extraction will be done after routing. And this RC extraction will be present in a file called as PEF file. So this file we will be using in STA, static timing analysis, to calculate the delay of our design. So once we know the real delays in our design, then we will be able to know the fixes of our design. If there are no more doubts, then we can wind up the session. And if you, if you still get any doubts in the future, then we can, you can post those questions in the group. I will be able to respond. Okay. Okay, then I'm ending this meeting. Thanks for joining. Thank you.